Welcome to our fifth Soil, Water, and Climate seminar of the semester. I will introduce today's speakers in a minute, but first I just want to invite you to join us again 2 weeks from today on April 14th, when our speaker will be Claudia Munoz-Zanzi, who's an associate professor in environmental health sciences here at the U of M. So please join us again for that. But today I have the honor of introducing our graduate student lightning speakers. We have Louise Allen, Jonathan Birkel, and Manny Sabbagh. Louise and Manny both work with Melissa Wilson, and Jonathan works with Tracy Twine. So we're happy to have you three here today, and I'll go ahead and turn it over to Louise to start us off.
Thank you, Kelly. Share the screen first. You see that?
Yep, looks good.
Hello, everyone. Again, my name is Louise Allen with Dr. Melissa Wilson. And today I'll be talking about winter manure management for water quality. So manure has a lot of benefits to it, and one of the main components of these benefits are going to be soil health. So manure has a lot of soil organic matter, 20 to 80% of dry matter, which contributes to microbial activity being spurred by this organic matter. And then this microbial activity, of course, helps with plant nutrient uptake and aggregation as well in the soil. So aggregation will then have more soil health benefits, of course, like infiltration and water holding capacity, etc. So a lot of benefits with manure. But then one of the reasons why we are interested in this research is also because of water quality. So how can winter manure best management practices contribute to water quality? And of course, we're in Minnesota, so we don't have any shortage of manure. This is a graph just from this January 2021 from the USDA. And you can see that on any given year, we have at least 2 million cattle in the state. However, this manure has to go somewhere. And so in Minnesota, manure travels on average just about 1.3 miles. So from the source, and it's applied, of course, near the source. There was a really interesting survey by the Minnesota Department of Agriculture to farmers. And so farmers, about 28% of farmers had stated that they apply manure during the winter. And so they could apply this on a daily basis, sometimes on a weekly basis. It depends on their storage. And so storage is, of course, a reason why they apply it is because there are many farms who have been in the family for generations, and they just don't have adequate storage or enough storage to hold the manure during the entire winter. And so they then have to apply it instead of holding it for the spring. And so they will apply the manure on frozen soil, either below the snow or over the snowpack. And of course, that will melt eventually. And the snowmelt can occur in the spring, but also it can sometimes occur during the winter. And so that was one of the other motivations for our research, is that we have these changing winter conditions due to climate change. And so just to give you a couple of statistics, in Minnesota, temperatures for the month of January are about 4 degrees warmer than 100 years ago. And then we also have about a 5-time increase in the frequency of freeze-thaw cycles for the month of January as well, since 1950. So weather is unpredictable, climate is becoming increasingly unpredictable. And so this is our field study. Our study is luckily in the St. Paul campus, in one of our plots on campus. And so we have a few research questions. One of them is whether the timing of the manure application during the winter will affect the snowmelt runoff nutrient content and loading. And then if these nutrient dynamics are going to be different when the manure is applied at different times and exhibit different loss patterns. So these two questions are part of one of our studies that we are doing. The third question has to do with a different study that we did as well, and that deals with the location of manure within the snowpack and whether it has a different nutrient loss pattern depending on where it is in the snowpack. But for this experiment, we have 3 treatments. So we have no manure on these small plots. These plots are about 1 meter long. And then we have manure under snow applied in early winter, and then manure over snow on late winter. We have these 3 treatments across 9 plots. And so this we have, for example, on 1, 2, and 3, we have manure over snow, no manure, and then manure under snow. And then the manure application rate that we did for the plots was approximately 147 kilograms per hectare for total nitrogen, and then about 33 for total phosphorus. We applied the first treatment, manure treatment under snow or early winter on December 13th of 2019. And then we had snowmelt on December 30th. And so we had to sample at that time. Then our second treatment of manure over snow was applied in February of 2020. And subsequent snowmelt occurred twice. So we sampled in March twice. This experiment was also repeated again. So this year we did the whole experiment all over again for this winter. And this is what the plots look like after all the snowmelt is gone. So you can see here, for example, the manure over snow on the plot on the left, plot number 1. You can see the manure there. But then if you look at plot number 3, manure under snow, you can kind of tell that that manure is a little bit more incorporated in the soil as well. And this is a picture that I took myself of when I was preparing my samples for analysis. And I really like this picture because you can really see the colors and the differences in these colors, and hopefully that data will show something like that as well. What we analyzed for here was nitrate, ammonium, total nitrogen, dissolved reactive phosphorus, total phosphorus, and then dissolved organic carbon. So I don't have my data analysis done yet, unfortunately, but I will show you just some total averages that we found in the analysis. So here we have on the y-axis, we have a scale of about 18 kilograms per hectare of the runoff losses. And this is ammonium. So what you can tell here is that first manure application under the snow had higher losses on the first sampling, but then it is flat across, mostly flat. And then the manure over snow started out lower, but then it had higher losses overall. And then we have the total nitrogen on the same scale of 18 kilograms per hectare here. And again, we have this same pattern of the manure under snow having more losses for the first sampling, but then the manure over snow overcoming those losses. Then for the DRP, we are on a different scale at 8 kilograms per hectare on the y-axis. And so here again, it's just the same story that we had before, where the manure under snow stays relatively flat and the manure over snow has more losses of that as well. And again, this is just time down here. And then the total phosphorus has a similar story as well on the same scale here. And again, it's just the same story again. I hate to repeat myself. And then we have a completely different scale here on the y-axis of 160 kilograms per hectare for the dissolved organic carbon. So, but it still tells the same story again. So the manure over snow has more losses. And when we applied this manure over snow, I remember we measured the snow depth, and it was about 20 centimeters at the time when we applied the manure. So, yeah. And then we're also doing this other experiment. We repeated this experiment twice as well, once last year and then once this year. And we have 4 treatments in this case. And this concerns about the manure placement within the snowpack and whether that has an influence on the nutrient losses and the nutrient dynamics that occur within the snowpack. And so we have no manure on one of the treatments, manure under the snow, in the middle, and then on top. And these are 30 centimeter columns, and we have 3 repetitions of this as well. So in conclusion, I would say if, just looking at what we saw in the graphs, if you had to apply manure during the winter time, again, because of lack of storage most of the time, it looks like the early manure may be best for water quality. Again, the data will tell us eventually if this is significant or not, but it looks like, you may have better water quality if you apply that manure earlier rather than later. And then, of course, I would like to thank the contributions from these amazing people that have helped me with my research. Any questions?
All right, thanks, Luis. That was great. Folks can feel free to unmute and ask a question, or put it in the chat if you prefer.
Hi, Luis. Are you going to be sampling after? So it looked like you had sampling time to almost 90 days after application. Is that correct?
Yeah, about 100 days. Yeah.
100 days. Are you going to be continuing that sampling on the same plots, or how does that? Are you basically? It looks like you have 3 sampling sites with sampling times, rather.
Yes, right. So yeah, so we did repeat the experiment twice. So we did once in the winter of 2019-2020, and then once in 2020-21. But then we are done with that. Yeah.
Did you reapply to the same site, or did you go to a different site in 2020?
Oh no, it was on the same site. Yes.
Same
so we
site.
Repeated it. Yeah.
Yes. I see. Okay.
Yes.
All right. That's what I wanted to know.
Thank
Looks
you.
like, but you don't have the data for 2020. Well, obviously you don't have it yet.
No, right. Yeah, things are a little bit slow in the lab with COVID.
Okay. Thanks. Good job.
Thank you.
Any other questions for Luis?
Hi, Luis. I have a basic questions. Did you apply raw manure to the field?
Did I apply what? I'm sorry?
Raw manure. Well, yeah.
It was 20%. We applied 20% solids dairy manure.
Okay. Is composting a common practice?
Composting. Yeah, actually my advisor is looking at that right now, at composting manure, and I'm not sure if it's common in Minnesota. We have so much of it. It tends to be applied raw in the state.
Okay.
But yeah, my advisor is actually looking into that right now.
Okay, thank you.
But yeah, it's a good question because I wonder if composting could help minimize those losses and better for water quality.
All right, I'm not seeing any other questions in the chat. So how about we move on to Jonathan, and then if other questions come up, we should have a little time at the end if you think of other questions for Luis. So go ahead, Jonathan.
Okay. All right. Thank you. And thanks everyone for virtually showing up. So a bit of a change of pace here before you hear more about Manure applications later from Manny. But my name is Jonathan Birkel, and I'm a second-year master's student in the Land and Atmospheric Science program advised by Dr. Tracy Twine. So for my talk, I'm going to be talking a bit about extreme heat events and some of their implications for public health, both in a general sense and more specifically in regard to how it's relevant to Minnesota and the upper Midwest and urban areas in particular. So to begin with, the thing about extreme heat is that it's a bit more of what you could consider an invisible threat than other forms of extreme weather. It doesn't leave, a heat wave can come and go and not leave the same kind of physical impacts behind that a flood or a tornado would, so people just often don't think of them in the same way. But in fact, extreme heat is the leading weather-related cause of death in the United States. And the links between heat and health are pretty well established overall at this point, but still in heat events, the mortality and morbidity that result from them is often underreported. And that has a lot to do with just what the incidents look like. Oftentimes, instead of something more obvious and easily attributable to the heat, like a heat stroke, you see an uptick in heart attacks or respiratory illnesses or things of that nature. So instead of looking on a case-by-case basis, often you can get a clearer picture if you look at just all-cause mortality during these events and how it goes above baseline levels. And as I'll be going into a little bit more later, there are specific categories of air masses that are particularly linked to summer excess mortality. So I'll begin by just giving an example of a heat wave that was particularly severe. This was Chicago in July of 1995, though it also to a lesser extent impacted Milwaukee as well. But this was a heat wave that resulted in over 700 deaths in under a week. And as you can see in this figure, it was the elderly population of the city that was particularly impacted. And in addition to that, if you break things down demographically, you can see there were a lot of racial disparities and that the Black communities of the city were particularly impacted by this event. And unfortunately, with heat waves, this often tends to be a pattern in other cities across the country, representing a wide range of climates. There's been studies in places like Phoenix, Arizona, or Richmond, Virginia, that have observed similar patterns, and often it has to do with the history of redlining. It's very tied in with that, and as a result of that, some neighborhoods just experience more heat stress than others, and it has to do with factors like tree cover or quality of construction materials or whether people have air conditioning. That last one in particular is a big one. So thinking about extreme heat and a place like Minnesota, you might think of Minnesota and picture something like this. This is what it looks like about half the year or close to it. This was a photo from my neighborhood just a few weeks ago. So you might think, why is this a concern here? And the thing about Minnesota and the upper Midwest is that we have a very high variability climate here, not just over the course of the whole annual seasonal cycle, but also intra-seasonally. So it's less consistently hot throughout the summer than a place like, for example, Arizona, where you're going to see a lot more days that that surpass a given temperature threshold, like say 95 degrees Fahrenheit. But people who live there are a lot more acclimatized to those kinds of conditions. So even if we have fewer days that reach a threshold like that here, any one of those days is going to put a lot more people at risk. And there's a lot of metrics out there for evaluating the severity of heat waves, but there are some, like the Nairn-Fawcett excess heat factor, that are intended to specifically account for acclimatization and mean a bit more when it comes to health outcomes. So if you look at this figure here, it's showing the mean positive values for this excess heat factor, and you can see a strong relationship with latitude there, where in the southern portion of the continent, it has a more highly variable mid-latitude climate as compared with the tropical climate in the north of Australia. So for this excess heat factor, it's really just, it's pretty simple. It's a combination of these two components. So first of all, you have a significance index where you're looking at the average temperature over a 3-day period and seeing how much that exceeds your 95th percentile for daily temperature. And the fact that it's a 3-day period is important because the impacts of heat are cumulative. So 3 hot days in a row are going to be more damaging than 3 non-consecutive hot days. So this second index here is the acclimatization index. So that one, you're just comparing your temperature over a 3-day period to the temperature of the 30 days preceding it. So you're generally going to see a higher value there earlier in the summer than later when it's been hot overall for a longer period of time already, so people are more acclimatized. And then this factor is just a product of those two indices. But this is just one of any number of metrics for evaluating things like this. One thing that's important to note when looking at temperature, when looking at extreme heat events, is that how hot it gets during the day is not the only important thing. You'll also have to consider nighttime temperatures, because if you have cooling at night, then that provides relief from heat. And so looking over the last 75 years in Minneapolis, you can see that daily highs have not really changed all that much, but there has been a marked increase in the daily low temperatures. So that leads to a narrowing of the diurnal range. And I should note these are summer temperatures from June 1st through September 15th. So we're just averaging for each year from those days. And you might look at this and think that, oh, maybe this is a result of climate change, but really it has a bit more to do with the urban heat island. And when we talk about extreme heat events, it's very common to particularly focus on urban areas, and that's because they tend to be hit the hardest by these in terms of excess mortality. And a lot of that has to do with that lack of nighttime cooling that you get as a result of the urban heat island effect. You can see the urban-rural difference in this particular figure for the MSP metro area is quite a bit more drastic at nighttime than in daytime. And as an example of that, looking over the past 75 years, we can see differences in the diurnal range if you compare the Minneapolis airport, which is fairly near the midpoint or the center of the metro area, whereas Jordan is a town to the southwest that's, you can see it's kind of right on the edge of the influence of the urban heat island. And there's a difference between those two when you look at changes in the diurnal range over this past period of time. And so while climate change may not be the main driving factor as of yet, it's definitely something that we can expect to see making a bigger difference going forward. And so these are some outputs from downscaled models that my advisor, Tracy Twine, and others in our lab have been working on over the last several years. So this is downscaling from 8 different general circulation models that we have that downscaled to a 10-kilometer grid. And so we have a simulated version of the late 1900s, and then we have, this comes in 20-year periods, so that's 1980 to 1999, and then we have one for moderate emissions in the mid 21st century. And then we have two separate versions of the late 21st century representing two different emissions scenarios. That's moderate emissions is RCP 4.5 and high emissions is RCP 8.5. So as you can see, if emissions don't get reduced and they stay high over the century, then we can expect a lot more of these really hot days. But the thing about temperature is it's just one element of what the human body experiences. And so only looking at that doesn't really give you a complete picture. What instead is helpful is to look at weather situations, because the human body really experiences a whole ensemble of weather elements all at once, and you can aggregate those into different categories of air masses, some of which come with a higher risk than others when it comes to heat and health. So you might see a resemblance if you're familiar with a more traditional air mass categorization system. But this is a little bit different because there's some additional categories. There's also a dry moderate and a moist moderate, in addition to the dry polar and moist polar, which, for example, would correspond to the typical continental and maritime polar, and et cetera. But it's really the dry tropical and moist tropical, and even more so the moist tropical plus, which are considered oppressive when it comes to heat. And moist tropical plus is just a subset of the moist tropical air mass, where your apparent temperature is greater than 1 standard deviation above what's considered a normal or seed day kinds of conditions for that air mass. So basically the point of this is to break down climate trends in a way that's more meaningful to how the human body will respond. And importantly, it's based on localized thresholds, because as we've seen with acclimatization, that matters a lot. Depending on where you are, the same conditions won't have the same impact. So if we break things down a little bit by air mass types, we can see that trends over time are not consistent across these different types of air masses. Here we're comparing the hot and moist, or MT days, to the hot and dry, or DT days. And we can see that DT days are not really, they haven't been changing much over the last 75 years, whereas these MT days have had a small but statistically significant increase over time. And I'm not showing the highs because those have either stayed pretty consistent or in a few cases actually decreased. But what's also important to note is how often these air masses occur. And with the DT on the right, we can see those are not all that common in this region. We tend to see less than 10 of them per summer, whereas the MT days are one of the more dominant types in summer, and they're increasing in frequency. And that's mainly at the expense of the dry polar types, which are cooler and less humid. So that's something to keep in mind when you're looking at shifting climates in a given region, is the shifting dominance of air mass types. And if some are more threatening to health, while others that provide relief are decreasing in frequency, then that's important to note. So how would this all translate to health outcomes, though, is a big question here. And to illustrate that, these are some data from another project that I'm involved with, looking at heat and health in Madison and Milwaukee, Wisconsin, which in terms of air mass frequency are fairly similar to Minnesota. So as we can see, the DT and the MT plus are particularly oppressive, as they often are in many circumstances, where in the case of DT, especially for total mortality, not dividing by age, that's about 3 deaths per day, or almost, above the baseline, and which is about a 10% increase. And as you can see on the right, the DT and the MT plus are not very frequent in terms of how often they occur, but they do make an outsized impact on health. And it's also important to note, if you look at the difference between total mortality and mortality specifically among people 65 and older, that there's a difference there. The DT days, since there's not as much humidity to keep the temperature down, those often reach the highest temperature of any air mass, and those days are particularly harmful to people who spend more time outside, especially people who may work in an outdoor setting. Whereas if you look at the MT plus days, those are the really hot and very oppressively humid days, which are more likely to impact elderly people who are more likely to be staying inside, but especially if they don't have air conditioning, then that can become a problem. So going off of that, some of what my ongoing work concerns is taking these downscaled climate models that we have and using their outputs to produce daily synoptic classifications going forward, and trying to see how we can break some of these trends down further. Because one thing we can do, as shown here, this is an example of just average summer minimum temperatures. So we can see that especially by late century, if we have a higher emissions scenario, those nighttime temperatures are really going to go up overall in the summer. But like I said, these kinds of trends tend not to be uniform across all air mass types. So what we're hoping to do is see how the frequency of those oppressive air mass types will increase going forward and what the temperature trends will look like within those days, as well as a consecutive day analysis, seeing if more of those heat wave days occur in a row relative to what currently tends to happen. So while I'm on the subject of these downscaled projections, I should point out that they're useful in a lot of different contexts. And this is an example of another project that I'm involved with that's dealing more with precipitation frequency. We're trying to imitate some of the calculations that NOAA has made for their Atlas 14 depth duration frequency estimates. So this is an example of what some of their data products look like, where given a depth and a duration, you can see how often that's likely to occur. So for example, if you look at the 7-day duration, you can see that roughly every other year you can expect rain occurring up to 4 inches within that time frame. But as a much lower probability event, like say every 1,000 years, you might see closer to 14 inches in that same time frame. But this is all calculated based on the assumption of a stable climate. And obviously that's not an assumption that really holds anymore. So we're trying to see how climate change might make these curves look a little bit different going forward into the century. And it's kind of a statistical challenge to imitate their methods when we're dealing with model outputs that just have 20 simulated years at a time. So it can be difficult to produce reasonable results from that. And that's kind of an ongoing project, but just an example of how versatile these model outputs could be, you know, temperatures and how they might look different. And it also affects like the sort of thing that Luis was talking about with freeze-thaw cycles and soil temperatures. So it's all very connected, and the more we can look at how things are going to change, then it's all very useful. But the idea in any of these cases is that we want to have usable results that can be practical in some format. So for precipitation frequency, that's very relevant to stormwater infrastructure. But in the case of heat and health, a lot of the solutions there and approaches that cities can take kind of fall under the umbrella term of cool cities solutions. So that includes things like increasing the tree cover within an urban setting, or increasing the reflectivity of urban surfaces like pavements or roofs. And so by cooling the air above these surfaces, essentially the idea is that you're hoping to you're hoping to transform a more oppressive air mass into a more benign type. And sometimes, especially if you're near the threshold of one air mass type and another, then even small changes can really save a lot of lives. And so that's the goal, is for cities to be able to do that a little bit better. But in order to do so and make more effective changes, they really need to understand the risks on a more local scale. So thanks everybody for listening. And now I'd like to open it up if anyone has questions.
All right, thank you, Jonathan. Again, if folks want to either unmute, or I'll keep an eye on the chat as well.
I have a quick question. This is Fabian. I was just wondering, in terms of the heat generated in the cities, how much of it is, you know, sun radiation that is absorbed by like pavement and things like that versus generated by human activities like cars and condensers or things like that?
Yeah, that's a great question, and I'm not an expert on all the dynamics involved in an urban heat island, but it's definitely a combination of all those things. But in particular, it's the extra heat that's absorbed by urban surfaces relative to what would be absorbed in a more natural type of land cover situation. So you have all these, you know, you have pavement and concrete and everything. Those absorb a lot of heat and then release it back out into the air more slowly at night. And that's why, particularly at nighttime, you see those bigger urban rural differences in terms of your ambient temperature.
And if you had to name maybe a couple of low-hanging fruits to make changes that will be useful, impactful, but not super expensive, what would those be?
Well, another thing that I guess I didn't really mention, but that actually some of my work in these Wisconsin cities is geared toward improving is heat health warning systems, which are in place already and to some extent in like most cities and regions have some form of that already, but a lot of the time it's just they set some arbitrary temperature or maybe heat index threshold above which they issue a warning. But as we've seen, like that, there's a lot more at play that determines the risk of a heat event than just keeping it that simple with just only one variable in consideration. So there's other ways that you can implement a heat warning system that takes a bit more into account. And that's obviously something that doesn't require a lot of infrastructure changes. But aside from that, you know, it really depends a lot on where you are, because if you're somewhere really hot, like in a more desert city like Phoenix or Los Angeles, then planting trees may make a bigger difference, but also demand a lot of water that you may not have. Whereas somewhere like here, planting trees may help some, but there's more trees already present. So it all really depends on a lot of your other environmental circumstances. Any other questions? And here's my email address here, by the way. So if you think of something later and you're curious about it, then please feel free to let me know and I'll see if I can give you an answer.
All right, thanks, Jonathan. I think let's go ahead and move on to Manny, and then if we think of any other questions for Jonathan or for Luis as well, we can bring them up at the end.
Thank you.
Everything good to go on my end?
Yep, looks good.
So, hey everybody. So for those who don't know me, I'm Manny Sabbagh. I'm a second-year PhD student co-advised by Drs. Melissa Wilson and Paula Pagliari. And today I'll be talking about preliminary findings from my research, which seeks to develop best management practices for integrating liquid injected manure and cover crops. Luckily, Luis gave us a pretty good understanding of what manure is in terms of the different characteristics. But to guess like on an even playing field, manure is considered the feces and urine that is excreted by livestock, as well as the bedding material that is applied as a fertilizer source for agronomic production. In the upper Midwest, specifically Minnesota, manure is applied predominantly in the fall, with a smaller percentage being applied in the spring and even less in the summer. Manure can be applied onto the surface through broadcasting, injected, as you can see into the picture, as you can see in this picture where we have liquid injected swine manure, or surface application followed by tillage. Fall application is pretty common in the cold upper Midwest, specifically when the ground is at or below 50 degrees Fahrenheit or 10 degrees Celsius. This is because it inhibits microbial activity, which reduces nitrification and decomposition by the microbes in the organic matter. However, the early application of manure can still lead to significant losses through leaching, runoff, and volatilization. But a prior study done by our department actually shows that if you apply manure with tillage, you can greatly reduce the amount of nutrient loss during runoff events. And also applying manure at or near the surface can face losses through ammonia volatilization, but this is highly dependent on weather patterns and the type and the characteristics of the manure. There's a lot more ammonium versus organic nitrogen. Another reason why fall application is more popular among producers is that the chance of prolonged wet field conditions in the spring, like we saw in 2019, which can restrict heavy machinery from entering the field. However, spring application can occur in a timely manner. It can lead to lower chances of nutrient losses as nutrient loading coincides more with plant nutrient uptake or plant nutrient demand. Studies have also looked at side dressing manure, specifically liquid swine manure, during the early summer in corn systems, which show that it can provide equivalent yields as long as you apply the manure prior to the V4 stage. And this is in comparison to urea ammonium nitrate and anhydrous ammonia. So in this picture, you can see a liquid swine manure being side dressed in a on-farm study done in LAAS, Minnesota. Cover crops can be a pretty good strategy to reduce nutrient losses, as well as other services such as erosion control, weed suppression, nitrogen crediting, but it's all dependent on species type and the amount of growth you get out of the cover crops. However, in Minnesota, winter cover crop adoption is still low compared to other regions due to the harsh cold climate and the shorter cover crop growing season. And of the cover crops that are in use in Minnesota, cereal rye is probably the most common type, which is due to it being pretty efficient at taking up nutrients, especially nitrogen, and being winter hardy. So it can survive the cold winter months and come back in the spring and start growing again and fulfilling its life cycle. For the studies that look at cover crop and manure integration though, generally manure is applied prior to cover crop planting. This still leads to a great risk of nutrient loss as there are no active roots in the soil to take up nutrients and possibly shortening the cover crop growing season even more. So our study seeks to determine the impacts of first planting a cover crop and allowing it to grow prior to applying manure to lengthen the cover crop growing season. So here in the picture, you can see me taking samples of what looks like cereal rye in the spring prior to termination. And we will go into this further, but there is a pretty good stand of cover crops this past year. As such, our objective is to evaluate the impacts integrating cover crops and manure have on soil health, nutrient cycling, and agronomic responses in 2 rotation systems. One is a sweet corn followed by grain corn and a soybean followed by grain corn. Each site for the rotation were conducted on small plot studies at the University of Minnesota, Southern Research and Outreach Center in Waseca, Minnesota. The studies began in spring 2019 with the planting of either sweet corn or soybean in their respective sites. First, I want to talk about the sweet corn rotation. Like I just mentioned, this was first started in spring 2019 and then it ended in fall 2020 with the harvest of grain corn. I'll take you through the cover crop, row crop, and field management practices and what findings we have to report on thus far. And as well, we try to mimic management practices that are commonly done by producers in this area. So for the sweet corn rotation, this study involves a randomized complete log design with split plot. The main plot or whole plot is nutrient source. We have early manure application applied at the end of September, a late manure application which is applied at the end of October, and a no manure treatment that received urea in the spring prior to grain corn. Again, this is more of a control because applying urea is more of the standard practice by producers. And the subplots were the cover crop type, which included single species rye, cereal rye, single species common oat, and a rye oat radish mixture, and no cover crop. Cover crops were drilled right after sweet corn harvest and chemically terminated and tilled under approximately 2 weeks prior to grain corn planting. The early manure treatment was chosen to see if we could apply manure early in the fall season and see if cover crops influence nutrient uptake and agronomic responses compared to no cover crops. And the late manure is the conventional practice of applying manure when soils are at or below 50 degrees Fahrenheit or 10 degrees Celsius. The manure type was finisher swine manure. It was injected with sweeps to minimize soil disturbance up to 6 inches, as you can see in the picture. We applied 183 pounds nitrogen per acre, which was applied as 143 pounds per nitrogen per acre in the fall through manure, which is the first year available nitrogen, and 40 pounds of nitrogen per acre through starter fertilizer in the spring. The no plots with no manure received urea nitrogen fertilizer in the spring at a rate of 183 pounds nitrogen per acre to ensure nitrogen was not limiting in any plot. So moving on to preliminary findings, we have here cover crop biomass accumulation or yield in the spring prior to termination. On the y-axis, we have the weight of the cover crops per area presented as pound per acre. And on the y-axis, we have the cover crop type. As expected, the single species rye actually had the highest amount of yield compared to single species common oat and the rye oat radish mixture. As mentioned previously, rye, which accumulated around 800 pounds per acre, is a winter hardy species and tends to overwinter and continue to grow quite rapidly after optimal conditions reoccur, so when spring happens again. Whereas oat, it has a more robust growing pattern early in the fall season, but tends to slow as its life cycle continues. But oat is a very winter intolerant plant, so once you hit that 32 degrees Fahrenheit and below, it it basically dies and does not survive the winter. The mixture had the second greatest amount of yield due to it having rye in the mixture itself. So again, the mixture was rye, oat, and radish. Yeah. For grain yield, we have bushels per acre on the y-axis and the nutrient source on the x-axis for the left graph. And for the right graph, we have yield on the y-axis and the effect of cover crops on the x-axis. The fertilizer treatment was applied in the spring and was applied at similar rates to what the manure plots received. So again, that's the urea, which is the standard practice of applying nitrogen for corn production. And in general, there was no interaction between the cover crops and the and manure, but we did see that late manure application, as you can see in the left graph, had a lot higher yields compared to early manure and the urea fertilizer. I don't have data shown here, but we saw that the nitrogen remaining after manure application in November, there's a lot more nitrogen remaining in the soil compared to the early manure. So that could be a reason why there's a lot higher yields due to more nitrogen retention. And as well, for the early manure, we might think that since it was above the threshold of, inhibiting microbial activity, there's a lot of maybe losses that could have happened during an early fall season. And so moving on to the right graph, that looks at the effect of cover crops. There's a trend that rye may be reducing yields by about 15 bushels compared to no cover crops or oats, but more in-depth analyses are needed to find why there is a trend of rye reducing yields. But studies have shown that corn following rye can reduce yields due to nitrogen immobilization. But hopefully we're thinking that the soil health benefits that rye provide may offset the reduced yields, but more to come on that. But all in all, though, yields are pretty good for the cover crop treatments for this past year. Now moving into our second rotation, which is the soybean followed by grain corn. Like sweet corn, soybean was planted in spring 2019, followed with cover crop planting and manure application, and then ending with grain corn harvest in fall 2020. And again, we also tried to mimic the common production practices that are utilized by producers for this region. It's gonna be a little repetitive in terms of the sweet corn rotation, but here we have a randomized complete block design with split plot. The main plot or whole plot is nutrient source, which includes manure or urea, manure applied in the late fall, around late October, or urea applied in the spring prior to corn planting. The subplots were cover crop type, or cover crop planting method, which were single species cereal rye, which was overseeded by hand during the soybean leaf drop, as you can see in the picture to the right, to simulate aerial seeding or through a high boy seed spreader, or drilled after soybean harvest. The cover crops were chemically terminated in the spring and tilled under approximately 2 weeks prior to grain corn planting. And the manure was applied when soils were at or below 50 degrees Fahrenheit or 10 degrees Celsius. The manure, again, was also a finisher swine manure, which was applied through sweeps to minimize soil disturbance up to 6 inches. Nitrogen was applied at 138 pounds of nitrogen per acre due to a nitrogen credit from soybeans. So 98 pounds of nitrogen per acre was applied in the fall, and 40 pounds of nitrogen per acre was applied through starter fertilizer in the spring. The nitrogen applied in the fall through manure signifies the first year available nitrogen. The no manure plots received urea nitrogen fertilizer in the spring at a rate of 138 pounds nitrogen per acre. When looking at cover crop yield in terms of pounds per acre on the y-axis between the drilled and overseeded cover crops, the overseeded cereal rye significantly did better than the drilled cereal rye. Drilling the cereal rye after soybean harvest seemed to have greatly inhibited the growth and production of cereal rye, so it may be best to plant cover crops as early as possible to allow enough time to grow and accumulate enough biomass in the spring. Although the data also, we don't have any data for this, but when looking at if overseeding the cereal rye can affect soybean yields, we actually saw there was no effect of yield, where we saw all yields were significantly, statistically the same between overseeded, drilled, and no cover crop plots. For grain yield, we have bushels per acre on the y-axis and the nutrient source on the x-axis for the left graph. And for the right graph, we have yield on the y-axis and the effect of cover crops on the x-axis. Unlike the sweet corn rotation, the only treatment effect that we have is the cover crops. So when looking at the nutrient source on the left graph, there's not much of a yield difference between the fertilizer, urea, or late application of manure. But when you look at the right graph, we have we see that no cover crops have a slight edge over the overseeded and drilled cereal rye, where yields are about 12 bushels per acre higher with no cover crops, but with the 2 cereal rye treatments still having, but there's still good yields happening, or still enough yield accumulation in the 2 cover crop treatments. And again, as mentioned before, rye can impact corn yield in a negative way, but with the still high yields, the alternative benefits that rye has, such as weed suppression and erosion control, can have a greater impact down the line. A more in-depth analysis is needed to see why the yields are lower with cereal rye planted and if they have a soil health benefit compared to no cover crop planted. Preliminary findings show that planting cover crops as early as possible is the best for promoting enough biomass growth. Rye did have a small penalty against corn grain yield, but soil health benefits that rye may be able to provide may offset these yield reductions. And again, I've done all this research without a great team, so I'd like to thank Jeff Vetch and all the personnel at the Southern Research and Outreach Center in Waseca, Minnesota, the Wilson Lab for helping with data collection and lab support, and the Minnesota Corn Research and Promotion Council and the Foundation for Food and Agriculture Research for providing funding. Thank you. Any questions?
Thanks, Manny. That was great. Again, I'm watching the chat, but also feel free to unmute.
Hi, Manny. This is Carl.
Hello.
Just a quick question. In terms of the termination, was that, you said it was 2 weeks before planting, but in the spring, but can you give me a better idea of when it was terminated? Like the date, around the date?
I don't have the exact date, but it's more towards the later April time.
Okay, so later April.
Yeah, so we also wanted to also kind of terminate the cover crops as late as possible so we can get that enough, just that little extra biomass growth from the cover crop. So that's also why we kind of like, we're pushing the date a little bit.
Yeah, I did the same thing in some of my studies, although I did not see the negative effects of rye that you had. And it's kind of interesting. Particularly with the soybean one, where you didn't really get much biomass and you're still getting a negative effect.
Since that was like kind of like we're kind of like, you know, skeptical like what's happening. We actually did a around the V7, like a pre-soil nitrate test to just look at what is the nitrate and the ammonium levels at that time. So maybe that can give us a better picture of why there's a yield reduction when there's cover crops, or even when there's no cover crop, even being able to grow like in the drilled cover crops in the soybean plots. So
Yeah,
hopefully you can give us a better picture or get a better idea or answer why that happened.
Yeah, I would find it hard to believe. I think you only had 250 pounds of biomass with the rye, with the soybeans. And yeah, so that's not, I can't imagine that you'd have much tie up, but I guess you never know.
I mean, and also like the rye was pretty green. So like you look at studies that show that, you know, the C/N ratio is a lot lower when it's, you know, still in the vegetative state, when it's like a lot more mature, when it becomes like more, you know, golden or yellow, where it has a lot higher
Right.
C/N ratio.
Yeah, yeah. The measurements I've made, there's usually about a C/N ratio of 15 at that stage. So it's hard to explain it based on nitrogen. Did you do any, I guess you only have one nitrogen rate, so you really don't know if you could compensate for it with a higher rate of N. So
yeah, so maybe that's something for future research.
yeah, I guess so. Okay, good job. Thanks.
So just a question and a comment too, I guess along the same lines of what Carl was mentioning. We have seen with rye also in one of our sites, is a sandy irrigated site where we do have a response curve to nitrogen, and we've noticed that in general we end up needing more nitrogen with rye than not rye as a cover crop. Not a lot, but something like 12, 20 pounds extra on average. But the question I guess I have was, you showed that with rye you have this yield reduction, but not so much with oats. And again, just like you were mentioning, or Carl was mentioning, that the C/N ratio is probably not sufficient to tie up a lot of nitrogen. Have you looked into any of that to see why there is a difference between the rye cover crop versus the oat cover crop?
Oh, I mean, we're still conducting analyses. We're looking at different soil health parameters, you know, different physical, biological, and chemical parameters. So maybe we're not exactly sure what's going to happen or what is happening, but something that we need to like really think about more and more, and see if there's ways we can look at it to see why there is that oat versus rye penalty.
Yeah, I wonder if there is some kind of toxicity or something like that. Phytotoxicity or something like that may be impacting I really don't know. I suspect that there shouldn't, but between the two species, but I don't know.
I mean, also, like, you know, rye is well known for being a very allelopathic and weed suppressor, but the studies have shown that the allele chemicals aren't strong enough to, you know, hurt big seeded plants like corn. So they don't really see it affecting the corn plants, but maybe there is some kind of underlying processes that's happening biologically or chemically.
But I believe most studies, they say that with 2 weeks of termination, typically you overcome some of those phytotoxic impacts. So anyway, I don't have any good answers, just questions, I guess.
All right, I see we're just past 4:30. I want to really thank all three of our speakers for volunteering to do this today. I really like hearing from all the students in the department, so thanks for your talks. Those were all great. Any final quick last question for any three of our speakers? Thanks for all the claps. All right, well, if not, thanks again for being here, and hopefully we'll see you all back in 2 weeks. Bye all.